Hello everyone, I hope you're all healthy and safe. Today we start a new topic, support vector machine or SVM algorithm for machine learning. So we talked about artificial neural networks in the past 2 weeks. Now we will cover support vector machine, a new very important and popular algorithm in machine learning. After that, we will talk a little bit about dimensional reduction and feature selection. And after that, we will return back to artificial neural networks with more advanced topics in deep learning and convolutional neural networks and so on. Support vector machine is a very popular machine learning algorithm originally invented by Vladimir Vapnik. It is one of the most accurate supervised learning methods. The algorithm is simple, but it can even beat artificial neural network in some cases with manually created features, I mean handmade features, and a small data set, especially when the data set is a small. And SVM can, in some cases, can provide even more accurate results than artificial neural networks. It was originally a linear model, but later some other articles suggested a way to convert linear SVM into nonlinear SVM using kernel trick that we will cover later. SVM became famous when it achieved an accuracy comparable to artificial neural network using hand-designed features in handwriting recognition. So, for many years, artificial neural networks was the most popular machine learning algorithm and provided the best results at the time. But as you know, artificial neural network is very complex. At some point, scientists in this field, they felt that they hit a wall and they could not improve artificial neural networks accuracy anymore because they couldn't make it any deeper. They couldn't make more hidden layers to a neural network to make it more complex, because of vanishing gradient that I talked about last week, and also other problems. And also, as you know, artificial neural network is a very complex with many unknown variables. So we need to have a lot of data to be able to train it compared to other machine learning algorithms. And at that time, like 20 years ago, we didn't have that much data. So the data was very limited, and also the computational process was very limited. So scientists in the field of machine learning, they started thinking about other algorithms, and SVM was one of them, random forest was one of them, and they could achieve very accurate results with SVM for a small data set, even when we have a small data set for training, and it was very effective at the time. SVM is being used for a wide range of real-world problems. It's helpful in text mining, image classification, pattern recognition, and so on. It has been widely applied in science. Okay, it's very popular in science. So biology, you will see that even biologists or medical doctors, they use SVM algorithm for their application. In chemistry, in bioinformatics, astronomy, business, finance, it is very popular algorithm for many different applications. And as I mentioned, people in different fields, like a biologist or medical doctor, you see that they are familiar with SVM algorithm. Generally speaking, SVM tries to find the best hyperplane, okay, or a set of hyperplanes in the feature space which can be used to separate data samples, to classify data samples. So by hyperplane, I mean a plane. So in 2D, it can be a line when you have only two features. In 3D, it can be a plane. When we have more than three features in higher dimensional spaces, we call it hyperplane. So generally speaking, hyperplane can be your classifier in n-dimensional space. So this is a very simple example that we remember from before, classifying these samples, and using that we can predict if tomorrow or today is going to be rainy or sunny. So this is one classifier. So in this case, we only have, of course, in this very simple example, we only have two features. So your classifier will be a line. It will be a line in a 2D space. So how can we find the best classifier? This is the question. Is this the best classifier, or is this the best classifier? So there are infinite number of classifiers that you can use to classify these samples. So in this case, the samples are very ideal. They are simply completely separate, and they are distinguishable. We are able to classify them using a single line. In practice, the data is more complex, of course, but as you see, there are infinite number of classifiers that can classify these samples. But which one is the best? This is the main question. Is this the purple one or the blue one? Or maybe you think that this black one is the best one, right? Because it looks like it's in the middle, and it makes sense, right? SVM tries to construct a hyperplane or set of hyperplanes in n-dimensional space, in n-dimensional feature space, which can be used to classifying data samples. Intuitively, a good classifier can be a hyperplane that has the largest separation, or in other words, the largest distance to the nearest data samples of any class. This is called largest margin, or the maximum margin. So this is how the SVM works, the SVM algorithms. It tries to find the classifier that has the largest separation, largest distance to the nearest data samples of any class. So let me show you an example. This is our data, two classes, red and blue. And this guy is the nearest data point to our classifier. Okay, look at this area right here. This is safe zone. This is the area that there is no sample in that area. Okay, and we call it margin. So if you find the distance between your classifier and the nearest sample, okay, this distance, this is the distance to the nearest sample. If we double this distance from both sides, this is called margin. This is a safe zone that there is no sample in that area. For SVM algorithm, we are looking for the classifier, this line, that gives us the maximum margin. Among all of those classifiers, we are looking for a classifier for this line that gives us the widest green area here, the widest margin. So this is the main idea of support vector machine. So a good classifier can be a hyperplane Again, hyperplane in 2D is a line. In 3D, it is a plane. In more than three-dimensional space, we call it hyperplane in general. That has the largest separation, or in other words, the largest distance to the nearest data sample of any class. This is called largest margin. Given a decision boundary, or given this classifier, this hyperplane, we can calculate the distance between the hyperplane and the closest data points. If we double this size, we call it margin. So the margin is the widest boundary area with no data point in it. We would like to maximize the margin. So this is the goal. This is the idea that SVM classifier is built on, to find the classifier that gives us the widest margin. And it totally makes sense, because the data samples that are close to the margin, they are risky samples. They represent uncertain classification decisions. So the best classifier is the one that gives us the best maximum margin. So, well, this is the idea of SVM. So you know many different machine learning algorithms now. So from beginning, you have seen many different techniques and algorithms that we used. KNN, for example, it finds K nearest neighbors. Decision tree, we learned about decision tree. It sort the features based on the information they provide and build a tree based on that. We learned linear regression and logistic regression that was based on minimum loss function or minimum cost function in prediction. We use the same idea for artificial neural network too. And here we have a new criteria, maximum margin. So again, we have an optimization problem, but this time it is not minimization of loss or cost like linear regression and logistic regression and neural networks. It is maximizing the margin, so the area around this classifier. So this is what we want to do. So margin is the margin is the widest boundary around your classifier. The widest boundary before hitting a new any data sample. So this is a bad classifier. Okay, so this is the same data, another classifier. This is not a good classifier because the margin is very narrow. So look at these two samples. They are very risky samples. By a very small mistake or noise, for example, with a small mistake in measuring humidity, this sample will be on the other side of the line. Okay, so these are risky samples for our classifier. So in general, this classifier is much safer and provides the best results. All right, how can we do that? So this is the question. Now, among infinite number of lines, or in general, in n-dimensional space, infinite number of hyperplanes that you can find. So look, suppose that this is 3D, okay? So if this is your 3D example, so there are some samples here, and there are some samples here. You want to make a classifier that classifies them. So in this case, doesn't matter. So your classifier will be in the form of a plane when you have 3 features. Okay, so this is a plane now. So if it's 2D, it's a line. If it's 3D, it's a plane. If you have more than 3 features, in general, we call it hyperplane. So in a 100-dimensional space, you have to find the plane in that new space that classify these samples in that space. And there are infinite number of them, right? There you can draw infinite number of lines here, but which one is the best one? This is the main question. Which one gives you the margin. So of course, at some point we will have a maximization problem to maximize to make the value of margin as wide as possible. This is the idea. But how can we do that? So to do this, we need to learn a little bit about the vectors and matrices, because in support vector machine, as you can guess from its name, it considers each one of these data samples as a vector in the space. So look, each one of them is a vector. And this is a very useful approach. You will see, so each one of them is a vector. Each data sample in this case is a vector. And then it works with vectors rather than points. So in many different data science and machine learning problems, we use this approach. We consider our data points as vectors. So for example, in dimensional reduction, in recommender systems, and especially in NLP, in natural language processing, our data points, we consider our data points with vectors. We represent them with vectors and then work in the vector space. So I'm going to talk a little bit about it. Before we continue and see how support vector machine algorithm finds the largest margin, we need to briefly review some topics that we need from matrices and vectors. I'm sure many of you know these things from algebra class, but this is what we will just review the topics that we need for support vector machine, and then later for dimensional reduction, recommender systems, and natural language processing. And while I am reviewing these topics, I will show you, I'm going to discuss some examples in data science and machine learning and talk about how we use the idea of vectors to represent data samples in data science. So matrix, as you know, it's a rectangular array or table, a 2D table. Can be more than 2D, of course, but usually we know it as a 2D table of numbers, and we use this type of indexing to show each element of that. So I, J, so Aij means element of the matrix in row I and column J, okay? Row I and column J. You are familiar with different operations on a matrix, so summation or addition. For matrix, it is element-wise summation. Subtraction, it is also element-wise. Multiplication, to find the results of the multiplication between two matrices. This is the idea. The first element of the output will be the first row multiplied by first column. So generally speaking, the element Ij of the output will be the multiplication of row I of the first matrix element wise by column J of the second matrix. Okay, so this is the idea. And so this is the definition. And vector, that we are going to work a lot with vectors from now on. We can think of a vector as a directed line. It is in fact a matrix with only one column, but we can consider that in our problem as a directed line that has length and direction. So length and direction are the two features of a vector. It can be 2D or 3D or in n-dimensional space, generally speaking. So it can be, doesn't matter, there's no limit on that. So in data science and machine learning, you can consider a data sample as a vector, okay? And these axes are the features, okay? So you can represent one data sample, for example, today, okay, based on the three different features of today. So for example, based on temperature, humidity, and wind speed, you can represent the weather condition of today as a data point using these three features. Or you can represent, in medical applications, you can represent one patient or one medical condition using some features of that. Right? So we have always used this in our machine learning problems. Now we want to make it a little bit more formal. So there are these are the three different representation of a vector, as you can see. So this is the notation that I talked about before to make them separate. These are the standard notations that you can see in textbooks and articles and so on. Usually when we use a letter which is bold and capital and italic, it means that it is a matrix. So M and A are matrix here. When it is italic, lowercase and bold, it means that it's a vector. Okay, remember that. And when it is still italic but not bold, it means that this is a number, this is a scalar. So these are the three different notations that we use these are standard notations that we use in every article and textbook. You can see that. So vector addition, of course, because this is a special case of a matrix, the same rule applies for that. So the vector summation is element-wise summation. But here, if you want to show how does it work, so this is vector A, vector B. When I want to add them, I just need to draw vector B at the end of vector A. So this is another B. And then this will be A plus B. Okay. So this is how it works. So you may think that these are just pure algebra and why do we need that? Okay, but you will see that you use it in data science and machine learning a lot, especially in natural language processing. In natural language processing, in NLP, we just represent each word with a vector. Okay, so we have a set of commands called word to vector, okay, that just converts each word into a vector in the space, okay, and then we work with vectors in all of our processing. So multiplying a vector by a scalar, this is how it works. Okay, so when you multiply a vector by a scalar, as you see, it changed the length of that. If the value is negative, the direction will be on the other opposite direction. It can just change the length, or maybe the direction. If the value is negative, it goes to the other opposite direction. All right, subtraction. This is how you can subtract two vectors from each other. So this is vector A, this is vector B. If you connect B to A in this direction, this will be vector A minus B. Okay, so these are the things that I'm going to show you how we can use in machine learning later. Vector norm gives us the length of a vector. Okay, and of course you know it. It is just a square root of a squared, the summation of a squared of all elements. So this is how it works. It gives us the length of a vector. We also have norm 1 that has its own application. So rather than a square root, and this rather than a squared of elements, we just add them up, the absolute value of them. Okay, so let me show you an example right here about how we can, for example, in natural language processing, which is one of the most important applications of machine learning and data science these days, how we can use vectors to represent words. Okay, so you are familiar with one-hot encoding that I talked about before. So in one-hot encoding, we assign a code to each feature, to each value of the feature. So when your feature is categorical and get, for example, day of the week. Okay, day of the week, it has like 7 different values, Sunday, Monday, and so on to Saturday. When you want to use it as a feature in your machine learning models, you can do one-hot encoding. So for example, assign value of 0, 0, for example. Look, there are different ways to do it, but let's say the simplest approach. This to Sunday, and this, for example, to Monday, and so on. Okay, we do this one-hot encoding to represent, to convert a categorical feature into numbers that we can use in our machine learning model. So the problem with this is that you create, for this 7 values, you have to create 7 different features in your machine learning algorithm. So now when in natural language processing, in NLP, when we want to work with words, so we have hundreds of thousands of words. If we want to do one-hot encoding for the words, then we need to add hundreds of thousands of features to your algorithm, which is not doable. Okay, so another approach is to, rather than using like hundreds of thousands of features to represent words, we use a smaller set of words. So for example, 300 features. We use a smaller number of features. So for example, 300 features. We can represent every English word using 300 features uniquely. Okay? And these 300 features can represent every word. So these are features that can interpret, can represent those words. Different values of these 300 features can uniquely show a word. So for example, let me give you an example. Suppose that we have 4 words, let's say apple, okay, and then orange, and then king, and then queen. Okay, so these are 4 words that we want to show them using, let's say, 3 features. Let's say the color of them, I select a color, for example, let's say red. Okay, and then I select, well, let's say the other one is a taste, for example, sweet. Okay, and another one is something about okay, strong or powerful. So these are 3 features. So I use a 3-dimensional space. I cannot show more than 3D here. And these are 4 words, English words. I want to show them using these 3 features. So I have a 3-dimensional space like this. So let's say this is color red. Okay, this is taste sweet, and this is powerful, for example, strong. Okay, so let's look at these words. For the word king, for example, okay, color is not meaningful really, but strong, it is very strong. So there should be a point right here, maybe here. Okay, so this will be king. Okay, for queen, we almost have the same thing. Maybe it's a little sweeter than king, but the power is less. So maybe queen is somewhere around here. Okay, so this is a vector. So this is king. This vector will be queen. Queen. Okay. For apple, it is red. It is sweet, but it doesn't have. Strong is a meaningless feature for apple, so that's why maybe this is apple right here. Okay, and then orange is another feature. Maybe it's less red compared to apple and less sweet. So this guy will be apple, this will be orange. Okay, so you can show all of the words, all of the English words, using these 3 features in the space, in the 3-dimensional space, and using this and give values to that. So for example, for apple, we have these 3 features, right? So let's say the value, I normalize it in the range of 0 to 1. So for apple, maybe this value is 0.9, the value of red. The value of sweet is 0.8, and the value of strong is 0. Okay, for the orange, the value of red is like 0.8. It's less red than apple, less sweet, so I put 0.7 here. Strong is 0. Okay, for the king, color is meaningless, so 0 here. Okay, sweet, not really, so I give the value of like 0.1 here. Powerful, yes, it's very powerful, so 1 here. Okay, and same thing for queen, maybe 0, let's say 0.2, and a little bit less powerful than king. So this is how you can show every English word in natural language processing. This is called word embedding. Okay, word embedding. So you show each English word in terms of like only these 3 features. So we have 3 features here that we use to represent all words. Of course, 3 features, only these 3 features are not enough to represent everything uniquely, but using, for example, 300 features is a common thing. Using 300 features, almost you can represent every English word in a uniquely using this number. So this is 3D vector. Well, in practice, we use usually like 300D in natural language processing to show every word, every English word. And everything is a vector. Everything is a vector, every word. And we work with them. And we find a lot of things. So this representation gives us a lot of information. Okay? So this is a very interesting topic, to be honest. It was very smart way to work with words. And when we have these vectors, now all of the things that I talked about is meaningful. So for example, the angle between two vectors, okay, somehow gives us the similarity between these two. So when you have a word apple, this angle here, apple and orange, in this space, not necessarily in 3D, in 300 space. So this angle right here, it gives me this angle theta. It tells me the similarity between these two words, how similar these two words are. So this is one definition of similarity. You can have many different type of definitions. So for example, the subtraction that I just talked about, this subtraction difference between these two, this can also be somehow tells me the difference between these two. So the words apple and orange, they are very similar. The angle is small. So for king and queen, again, the angle is small. Okay? But if you have another completely different word, for example, computer, another word. So it has if you plot it in this space or in 300 dimensional space, you will see that it's very different. The angle will be high compared to these two. So this is one way to find out what words are similar or related or have the same meaning. Okay, so this is very important, and they have the same meaning. So it tells you two words that are they say they have the same meaning or have the same concept. This is different from words that looks like each other in English in terms of letters. So the apple and orange are completely different words, but the meanings are close. They are not necessarily synonym, but they gives us the same concept. We use these ideas in natural language processing. Okay, so this was just one example. I just wanted to tell you why you need to learn working with vectors when you want to do machine learning and data science. So this is the difference between two vectors that as I just mentioned, it can represent different things. All right, transpose, it's simple, just it's changing a vector or matrix, reflect vector matrix on a line. So so this is matrix, let's say this is matrix A and this is matrix A transpose. So as you see over this line, okay, I just replaced B with C. Well, this is what transposition means. Replace columns with rows. All right. So inner product is very important when we talk about vectors. So it's an operation. It's also called dot product. Inner product between two vectors define the inner. So this is the definition. This is the definition in n-dimensional space. Two vectors A and B, dot product or inner product. This is the summation of element-wise multiplication, or this is also equivalent to multiplying the length of the first vector to the length of the second vector times cosine of the angle between them. Okay, these two are the same. So summation of element-wise multiplication, which we can prove it is equal to length of the first one multiplied to length of the second one multiplied to the cosine of the angle between them. Okay, So it looks maybe weird, but you need this a lot in data science because it gives us the angle. So this is one way to find the angle between two vectors. Okay, so we mentioned that inner product is equal to this and also equal to this, so the cosine is equal to this guy divided by lengths. Okay, and theta, the angle between vectors, are important because, as I just mentioned, it is one metric, one very important and popular metric that measures similarity between two vectors. Okay, it measures similarity between two vectors, and it tells me how similar this A is to B. And there are many applications for that, many applications. So as I just mentioned, in natural language processing, if each vector is a word, then it tells me how those words are related. The meaning of those words are related. But there are many other applications for that. So for example, by the way, there are different definitions for similarity. This is one of them, one of the metrics that measures similarity. One important applications of that, very important these days, is in recommendation system. Okay, that you see these days everywhere, in every website that you, in every online shopping, for example, when you buy something, it recommends you to buy similar things, other things which are similar or related. In entertainment websites, for example, in Netflix, it recommends you to watch these movies because it thinks that you like them. Okay. So it finds the similarity between the item that you have purchased and the other items, and that's why it's suggested to you. And they are not necessarily similar. They are not the same thing. Okay, so remember that they are connected, they are related. So when you purchase a camera from Amazon, it does not recommend you to purchase another camera. Okay, this is not a smart way. It recommends you to purchase, for example, a camera bag or a memory stick or some other things which are related to your need, which are related to your purchase. And how does it learn? From what other customers did. Okay, from what, so it by time it learns that people who purchased a camera, they start searching for a camera bag, and by time it learns from data. So generally speaking, we have two types of let me open a white page. We have two types of recommender systems. We have so recommendation systems or recommender systems, as I mentioned, it's a very important topic and useful topic these days, especially very popular topic in data science and machine learning. So recommendation systems or recommender systems, there are many and different algorithms for that. It's not, again, it's not a single algorithm, but there are many different algorithms for that. But generally speaking, they are usually item based, okay, recommendation systems, or user based. Okay, two types. So item based means that when you buy an item, okay, the algorithm recommends you to buy another item which is similar to this item. something like that. So it is like, for example, when you watch a movie on Netflix, okay, the algorithm, the Netflix algorithm, it's not that simple, by the way. None of them are that simple, but I'm just give you the general idea. The algorithm suggests you to watch another movie which was similar to the first movie. Okay? So the item is similar to that. So you watch, for example, I don't know, one movie, and a horror movie, for example, and the algorithm suggests you to watch another movie, recommends you, it says the best found for you, for example, something like that. Because the new item was similar to the item that you liked. Okay? So if you watch, for example, Game of Thrones and you like it, and then it will recommend another series which is similar to that, has the same genre, has the same actors, for example, has the same story, something like that. It is based on similarity of items. In user-based approach, and it's different, okay? So you purchase, it recommends you to do something, it recommends you to purchase something because other users that are similar to you did the same, okay? So, for example, you purchase a camera, okay? Other users that also purchase a camera that were similar to you, they search for a camera bag or purchase a camera bag. That is why it suggests you to purchase a camera bag. So camera is not similar to camera bag. They are completely separate items. But the users that purchase camera, they purchase camera bag too. You purchase a camera now, so you are similar to those users. That is why it suggests you to purchase a camera bag. Okay, so these are two different approaches for recommendation, and they have its own application. Sometimes you want to recommend a similar product to users, to watch a similar movie, for example. Sometimes you want to recommend something that similar users did that. Okay, similar users with the same taste, with the same interest, they did that. Okay, so this is how it works. So recommendation systems, and in any of them we need to measure similarity anyway. If it is item based, whether it's item based or user based, anyway we need to measure similarity. There are different metrics to measure similarity, but one of the most popular ones in data science is this: the angle between. So each product, each movie in Netflix, or each product in an online shopping website, or each user, okay, or each movie, any product, it can be a vector, and this angle, so it can be a vector that we show them using some features anyway, in some feature space. So for movies, for example, you can define it like 100 features, okay, or 20 features that represents every movie. You can represent every movie using those features. So for example, I don't know, like genre, or the actors of that, or the story, or the directors, or whatever. So there are many features, and this angle between these two movies, it tells you how similar those movies are. And when you watch this and like this, then if this angle is small, the algorithm suggests you to watch this now.